have an apology to make. I've got a sore throat. My voice has started to go. So I'll keep talking this volume because I think that's a reasonable volume to keep me going for 15 minutes. And well, as you can tell from my introduction, I'm a composites engineer who's actually never used a CT scanner. But I'm going to tell you through this talk why I'm interested in CT scans. So the scope of this project is to assess the validity of fiber prediction models in typical process simulation method through CT scanning techniques. The material I'm particularly interested in is called carbon fiber SMC, and it might be not very familiar to many of you, even if you are in composites, because it's very different from conventional composite has got a long continuous fiber all perfectly aligned. But the material we use, as you can see from this picture, it's consisted of chopped carbon fiber, and it's all randomly orientated and distributed. And then this photo is actually from our SMC manufacturing line. So that's how this material is produced in the industry. It's got several advantages, although obviously because the fibers are chopped, we are not getting the same properties compared with continuous fiber composites. For example, with this kind of material, it can actually flow in the cavity, and that gives you great design flexibility because you don't have to stick with very planar geometry. But that also gives some additional challenges because the material is already random to start with, and then when you flow it in the cavity, that can introduce further variability. The example I've given here is a part where SMC has flowed into these side walls, and as you can see, the fibers are originally randomly orientated, but then starts to align due to the flow. And then that alignment can affect the properties in your final part. So it's very important to understand how the fibers will actually align or reorientate during the flow process for these kinds of materials. So the current challenges in process simulation and also structural simulation for SMC is this lack of dedicated material characterization method. So if you want to do a simulation, the first thing you need to do is to design an experiment to study the material behavior. And then that's then allow you to write a constitutive material model to build your simulation model. However, there's no robust characterization method for both the processing behavior and the structural behavior of the material, especially if we factor in the heterogeneous nature of the material, they are anisotropy because of the fiber orientation, and also size effect because for this kind of material, we're usually talking about fiber bundles that are 25 millimeter long. So in order to get a representative material behavior, you need a much bigger sample than the size of the fibers in order to capture the bulk material behavior. So you can't, for example, if you're measuring the viscosity of the material, you can't just take a very small viscosity sample like what you can do with polymer material. You need a much bigger sample. And because of the lack of dedicated characterization methods, material behavior has been poorly understood. And on another aspect is the lacking of fiber architecture characterization methods. So people have developed many models that they think can predict material behavior. But there's actually no evidence because if you can't have a robust and reliable experimental data to show here's the fiber architecture, you can't validate your model. So we are interested in CT scan. As someone already said in their presentation, as material scientists, we all know the benefit of CT scan. It allows us to inspect the internal architecture of the material, and also most of the CT scanning method is a non-destructive method, which means you can reuse the sample for some other forms of testing or analysis. However, there are significant challenges associated with CT scanning for carbon fiber SMC. So the first one, for those of you who actually do CT scan, I'm sure you understand the problem with low contrast between the density of the carbon fiber and the polymer matrix. So carbon fiber has a typical density of 1.8, where the polymer matrix we usually use would have something around 1.2. This means we need very high resolution to be able to distinguish the fiber and the matrix in a scan. And as I also mentioned, because the fiber inclusions are relatively large in size, we can't just scan a very small sample in order to resolve the fiber and matrix. We need to scan a very big sample, and that makes resolving the fiber and matrix even harder. And also because we want to analyze the final structure, which are usually much bigger than a typical very small CT scan sample. That's again a limitation in the size we can scan. And finally, the high aspect ratio of samples, because with this kind of material, we usually make shell or plate-like structure that's very thin in thickness. So my colleagues who are specializing in CT scanning, they did some parametric study to establish what's the optimum parameters you should use in order to get a reasonably good quality scan for a reasonably large size sample. So the samples I've shown here, they are 25 mil by 25 mil in size. The thickness are usually something around 2.5 mil. They vary slightly. And then they did this parametric study to change different scan settings and understand how each scan setting can affect the image quality. And they also did this local region scanning, because the idea is, even if we can't possibly scan a whole part, if we want to scan a small area that we are interested in the whole part, can we actually do that scan without cutting up the whole part? Then if we just do a local scan, then can we achieve a good image quality still, as if we are cutting the samples from the whole structure? So because I'm not CT scan expert, if you are interested in this study, we've recently published a paper with more details about these studies, and just read about it if you're interested. So I'm now going to talk about how the CT scan can actually support our work with regards to the composite simulation. So the first case study I'm presenting is a very simple flat plate geometry. And the way it's manufactured is we position the initial charge, which is indicated by the green box that's in the middle of the plug. And that's introduced a 1D flow regime, because the material can only flow in one dimensional. And that can introduce fiber alignment in only one direction. And I've given some parameter of the material we use. And we've also scanned 4 different samples from this plug, as indicated by the 4 red boxes. They are from similar locations, but quite different in the width of the sample. So one thing I want to notice at this stage is you can see this feature from the surface of the plaques molded, which is similar to a wild line as you usually see in polymer or composites component, but actually that indicates the edge of the ply, because when you mold a SMC part, you usually stack multiple plies of SMC. And with this particular material because the viscosity is higher than normal SMC. That creates a plug flow regime. So not all the plugs are flowing at the same velocity. Therefore, you can see the edges of individual plug from the surface of the plug. And as I said, we want to validate process fiber prediction models. So there are two commonly used type of fiber prediction models for this type of discontinuous fiber composites. The first one is a mesoscale model. They usually called direct fiber simulation. It works by modeling the movement of deformation of individual fibers, as you can see in this bottom image. So each fibers will be modeled as a chain of beam elements. The other one is a more old-fashioned model called Folger-Tucker. It's a phenomenological model. There are quite a few other models of this type where you don't actually model individual fibers, but instead you use a function called fiber orientation tensor. It means the probability of fiber alignment in certain direction. So you just you calculate the fiber orientation tensor on an element by element basis, and you generate a map of fiber orientation tensor rather than getting a physical distribution of fibers. So fortunately, both models are already available in commercial SMC simulation software, so that saved us the hassle to develop our model and program the fiber prediction models into our model. So in this study, we've just taken two commercial software that's got these two types of fiber models already embedded. So for the direct fiber simulation model, we've chosen the software 3D Timan. And for the Folger-Tucker model, we've chosen the software Modex 3D. Both are quite commonly used SMC simulation software. So firstly, let's have a look at the CT scan results. If you remember the 4 different samples we've scanned, that's got width of 25 mil all the way up to 100 mil. And as you would probably expect, as we increase the sample width, we are seeing a decreased quality, image quality, especially for the very wide sample. We are seeing these artificial stretch marks from the image surface due to streaking artifacts. And then this effect also creates problems in the fiber analysis because it's basically interpreted the results as fibers that's being aligned in that direction, although that's actually a visual effect caused by the poor image quality, where with the narrowest sample, 25 mil, we're able to get a very clear image, and the fiber orientation result is much more reliable as well. So I've then compared the CT scan results with the simulation. So when we were doing the CT analysis for this project, I gave my CT scan colleague a very long wish list I want them to do, like, can you segment individual fibers, and then gave me the information such as orientation, fiber wavelength, and how the toe geometry have changed. But they basically came back to me saying, with the current commercial software, fiber orientation tensor is the only results you can get. So, which was okay because we were still able to get some interesting information from it. And the one thing I want to notice is the plug edge effect I previously mentioned. This can be picked up in the CT scan as well. As you can see, it gives you a difference in fiber orientation distribution compared with the rest of the sample. However, this effect cannot be picked up by any of the simulation models I've put here. I've only put 3D Timan here because they actually gave you a mesoscale fiber architecture that can be compared directly with the CT scan, but the model cannot predict the plug edge effect. And also, we noticed something interesting from the edge of the plaque, if you remember where the samples were cut from. What we noticed is in the actual experimental plaque from the CT scan, you can see the fibers become very wavy in the edge area. And the reason for that is because compression molding of SMC is usually done at very high speed. So when your fibers crash into on the mold wall, that shock wave then gets propagated along the material. So you get a large area of material that's being affected by this edge effect. And that's actually very critical for SMC part because the majority of these components are molded net shaped, so there's no trimming afterwards. So you get this edge effect all along your component. However, in the simulation, it cannot really predict this effect. And the reason for that is in simulation, the fiber-fiber interaction is typically not considered. So when your first fiber hits the edge of the mold, there's nothing that's being propagated along the material. So it's got a very localized edge effect compared to in the experiment, you've got a much larger area that's being affected. And also in reality, carbon fiber is not a material that can withstand very high compressive stress. So the material can buckle very easily. Where in the simulation, because it's modeled as a beam, where the tensile modulus and the compressive modulus are equal, so you get a much stiffer response from the carbon fibers in the simulation. Therefore, you're not really seeing very wavy fibers, but instead, you're just seeing some slightly bending in the fibers. So we've also plotted the fiber orientation distribution along the length of the sample. So we've compared the results from the DFS and the Fokker-Tuck model, as well as the CT scan. So generally speaking, both simulation models over-predicted the level of fiber alignment. As you can tell, the values of the fiber orientation tensor in the horizontal direction is much higher than in the simulation. The DFS model, which is the mesoscale model, gives a slightly better prediction. And it's also nice that because of the way the model works, it gives you that random nature of the material so that you don't get the same results if you take the samples from different regions on your plaque. However, one thing I need to say is the Fokker-Tuck model is a lot less computationally expensive, as you can probably imagine. The 3D Timmer model would usually take a whole day to run, where the Fokker-Tuck model can give you results in a matter of hours. And so these are the areas that got a reasonably good correlation, although the simulation models still overpredict the fiber alignment. But the areas outside these two circles, so that area there is the flat edge effect where the simulations cannot predict. Then that area there is the model edge effect, which again, the simulation have been unable to predict the fiber orientation distribution correctly. And we then moved on to a more complicated case, which is a C-channel geometry, as I've shown here. And it's a 1600 millimeter long part. The wall thickness is 6 millimeters, so it's a reasonably large component. And again, we used SMC type of material. And the initial charge of this material is more interesting. We used a Swiss roll initial charge, which this is not how the part was made, but this is a good image to show how the Swiss roll charge works. You basically cut a big piece of material and then roll it up. So you can just mold the whole Swiss roll in one go. The benefit of this approach is you don't have to crop the fibers. and still be able to get a very narrow initial charge. So we did a process simulation for this approach as well. We use 3D treatment for this process, where it's not really possible to have a Swiss roll initial charge, but instead we just use a square prism initial charge to mimic the Swiss roll initial charge. And the initial fiber architecture was fully random. So here's the comparison of the results between the simulation and the CT scan. So with the CT scan of this part, we scanned one of the ribs, as you can see on the top right. With this particular part, we really had challenges to get a good quality analysis result because the image quality wasn't ideal. So we are missing quite a lot of data from the CT scan. However, there's still some areas where you can vaguely see there's good correlation, for example, around the edges of the part. But there's also in the middle of the rib where we are seeing more disagreements between the simulation and the CT scan. And the reason for that was mainly because in the simulation, we are seeing a feeling pattern that's quite different from what would happen in the reality, because as you can see, the last feeling point is along the top edge of the sample, quite towards to the edge, where in the actual CT scan, we're seeing the last feeling point around the middle as indicated by the wild line. So we think in reality, what happened with the flow pattern in this part is the material flowed along the sidewalls first before it actually entered the ribs. And then that difference in flow pattern will cause the difference in the fiber alignment distribution. So in conclusion, we've done some parametric study to develop the CT scan method, which allow us to scan the to perform CT scan for carbon fiber SMC parts for mesoscale fiber architecture analysis. We've done 2 case studies. The first one is a flat flag, where we found the image quality would under the quality of the fiber analysis would reduce with the increased sample size. And there's some disagreements between the simulation and the CT scan analysis results in terms of the fiber orientation distribution. And for the second case study, which is the C channel geometry, we were struggling to get good image quality to allow us to get comprehensive data of fiber distribution within the area we scanned. And we did some qualitative comparison, which suggests the disagreement in the fiber orientation between simulation and the CT scan were mainly caused by the difference in the feeling pattern. So I would like to end my presentation with the acknowledgement to the founders for this project and also my colleagues who have all contributed to the results you've seen on the screen today. So thanks for listening, and let me know if you've got any questions.